In today's video, we shall look at the physics behind the conical pendulum. So what is a conical pendulum? A conical pendulum is a weight or bob attached to a string or a rod. So the bob is right there, and this bob, it moves at a constant speed in a horizontal circle like that, thus tracing out the surface of a cone in a following manner as the bob moves. Here are some of the features. The first is the bob moves in a horizontal circle at constant velocity. Let's call it v. So horizontal circle. Feature 2. The bob, the string, and the pivot point trace the path of a cone. So feature 2 is conical shape. That is being traced out. Number 3. There are two primary forces that act on this bob. The first one is, of course, its weight. If the mass of the bob is m, the weight is mg. That is pulling it down. And the second is the tension in that string or the rod, which acts along that string or the rod. Such a setup is very useful in physics demonstrations to show crucial concepts such as the centripetal force. It also have applications in devices such as gyroscopes. To better understand the physics behind this conical pendulum, let's look at the first problem. The figure below shows a conical pendulum. The mass of the bob is capital M. The plane of its horizontal circular path is distance h below the pivot point. Find the period of revolution of the mass in its orbit in terms of just h. Let's assume the bob moves in a circle like that, and the radius of that circle is r. Let's assume the string makes an angle theta with respect to the vertical at all times. The constant speed with which the bob moves is v. So we can define period p as the circumference of that circle, 2 pi r, over that constant speed v. Now let's look at the forces. Now we know there are a couple of them. The first one is the weight of that bob, which is acting vertically downward, and the other one is the tension along that string, capital T. You see that the free body diagram of that bob looks like this. The tension is going in that direction. The weight is going in that direction. We note that this is a circular motion, a uniform circular motion. That means there must be a centripetal force towards the center of the circle, like that. We also see from this figure that this angle is also theta. So that means that is theta. So this angle there is 90 minus theta. Now let's write down the equations. Along the y direction, when we say the y direction, I'm referring to the vertical direction. X would be the horizontal direction. So vertically, this bob is not moving. It stays on that horizontal plane. So the net force along the vertical direction must be 0. So the y component of that tension must be balanced by the weight. From the diagram, you know the y component of the tension is just t cosine theta, that angle. So t cosine theta equals m times g. Now let's look along the horizontal direction, the x direction. There is the centripetal force, and something must provide that centripetal force, and that must only be the x component of that tension. So we write the x component of the tension equals the centripetal force, Fc. The x component of that tension is quite simply t sine theta. We note that this is tension, this is horizontal, and this is the x component of the tension, and we know this is 90 minus theta. That is this angle right there. So you see that tx over t equals cosine of that, or quite simply sine of theta. The centripetal force is simple. It's given by the mass of that bob, the square of that constant speed, over the radius of that circle. So let's put everything together. So this line here, it simply becomes t sine theta equals mv squared over r. Now if you take the x equation and you divide that by the y equation, you get tangent theta equals mv squared over r divided by mg, or 1 over mg. So m goes away and you get v squared over r times g. So tangent theta is v squared over r times g. We also know from this triangle, this is a right angle triangle, so r over h is tangent theta. So r over h equals tangent of theta. So substituting tangent theta as r over h, we get that. Rearranging the terms, you get r squared equals h over g v squared, or r is quite simply the square root of h over g times v. What that means is if you take the v to the other side, it will become r over v, and r over v is just square root h over g. Substituting this result in here, you see the period is quite simply 2 pi times square root h over g, and that is the answer for the period of revolution in terms of h. And that solves the problem. Now let's look at this problem. The conical pendulum shown below has a bob of mass 50 grams. The string length is 1 meter. The bob follows a horizontal circular path of radius 20 centimeters. Calculate the tension in the string and the period of the motion. So we know the free body diagram for this conical pendulum. The weight acting vertically downward. So changing the 50 grams into kg, so 50 divided by 1,000, times gravitational acceleration. So this is weight. This g here is 9.81, whereas that g there, to denote it is in grams. And then of course we have the tension in the string. Now note that this distance there is 20 centimeters. As we saw before in the first problem, the vertical direction forces, there are two. One is the weight and the other one is the y component of that tension, y being the vertical direction, x being the horizontal direction. So Ty equals 50 over 1,000 g. Now let's trace out the appropriate right angle triangle. This length is 1 meter. This one is 0.2 meter. So this length here has got to be, from Pythagoras theorem, 1 squared minus 0.2 squared square root. And that is the angle theta. And we know the y component of the tension is going that way, and the x component of the tension is going that way. So Ty, or the y component of the tension, is quite simply that. From this diagram, cosine theta is this length over 1. So we can write cosine theta as square root 1 minus 0.2 squared over 1, and that equals to 50 times gravitational acceleration over 1,000. And from this you can immediately find the tension, which turns out to be 0.5 newtons. So that is the answer for the tension. Next, let's do the period of the motion. We know from the previous problem, period is defined as 2 pi times square root. This vertical distance, let's call it h, over the gravitational acceleration. But we know what h is. H is just that, which we have determined from Pythagoras theorem. In other words, h is just square root 0.96. Substituting this number in here, we can find the period. That turns out to be 1.98 seconds. And that solves the problem. Thank you for watching.